Hey everyone. All right. So this video is going to try to cover all the important things about limits and just give you a quick refresher. If you need more, there are more videos down below from AB where I break it all down to the four major limit lessons I did. But this is going to try to remind you of the key things that you need to know going forward about limits. So essentially, I'm going to start with the graphical approach to remind you how limits work. Let's say you've got a function. And let's say we have this point here. It can be any point. You can call it 6, 7, 8. I don't. Let's just say we have this point. I'll call it A. Let's try to keep everything general. If I were to ask you, and we'll call the function f, what is f of A equal to? It is equal to whatever the y coordinate is. So let's say right here, that's the same y coordinate. We'll call that B. So the function value there is B. The input is A. When I plug A into the function, wherever the function is located gives you the output value. In this case, it's B. So that's a typical case. Then I can ask this question, though. What is the limit as x approaches A of the function? And that's asking a slightly different question. That's not concerning itself with what's happening at A. It's concerning itself with what's happening as the function gets closer and closer to A from both sides. So if I get closer to A from the left and I get closer to A from the right, do I approach the same y coordinate? Doesn't matter what it actually is there, but if you got infinitely closer together, what are your fingers, what y value are you basically getting closer and closer to? In this case, the answer is the same as the actual y value. It's B. This happens a lot. When there's nothing funny going on, when you have a completely continuous function, then the limit is going to equal the function value. So in a continuous function, this is always true. If the function is continuous, then the limit and the function always equal each other at any x value you choose. So that's the most boring case. What happens when things get a little more interesting? Well, let's say rather than have a point there, we have a discontinuous function, and we have something like this, where the actual value is somewhere up here. We'll call that up at C. Well, clearly this function is not continuous. There's a break in the function. So in this case, this is not true anymore. One of these things has changed. Well, if we talk about what is the function value at A, it is no longer B. If we look, the output is not here, it is up here. So the output is at C. What about the limit though? The limit, what are my fingers getting closer and closer to? Well, as I move along this curve, as I get closer and closer and closer to this spot right here, the curve is getting closer and closer and closer to the same y value it was when the function was actually continuous there. So it is still approaching B. So the thing I told you last year that was a key thing to remember is limits exist at holes, aka removable discontinuity. If you have a hole, you still have a limit there because your left hand and right hand are approaching the same value. It doesn't matter if the function is defined elsewhere or not. Our fingers are getting closer and closer to each other. You're approaching the same y value. So that's a graphical representation of how limits work. So when do limits not exist? Well, there are two other cases where a limit does not exist. That was the case of if you had something like this, where you have a left-hand limit that is different from a right-hand limit, where there's a jump in the graph. So this was called a jump discontinuity. This would be the limit not existing because the left-hand and right-hand limits do not equal. Or we have the other type, that was really bad, whatever, where you have something like this, which is called an infinite discontinuity because of an asymptote. The limit doesn't exist. The limit is undefined when you have an asymptote. So a jump or an asymptote, limit does not exist. Hole, limit does exist. No problem or no funny thing going on in the graph. The limit does exist. And so those are the cases of how you can think about where limits exist and where they do not. Okay, that's the purely graphical approach. So what about when we're dealing with sometimes I'm looking at my notes here. Sometimes we have a table, like we have a function, we can try looking at the table. So for example, if we were to try to figure out what is the limit as x approaches, I don't know, 2 of x squared minus 4 all over x minus 2. Here's a pretty classic Calc AB example. Well, there's lots of ways you can do this problem, and I'm hoping you remember some of them from years past. Well, last year. But here's a strategy we did not use a ton last year. It's probably the least used one. One thing you can do is you can actually try, and let's see if I can figure this out. 1 second. I'm on Desmos. I'm just gonna bring it down. You can try and graph the function x squared minus 4 all over x minus 2. And we're asking what's happening at 2. Well, if you look, the function's undefined there. It looks like there's a hole, but look, the function's approaching the same y value from both sides. So it looks like the answer is 4. It looks like the y coordinate that wants to be there is 4, which I can show you in a second algebraically how that works. But is there a way to do this from the graph? Yeah, you can play with the graph and see, look what's happening from the left. As I get closer and closer from the left, look at that y value. I'm actually going to zoom way in. What y value am I getting closer and closer and closer to? Well, look, I'm getting 3.9, 3.99, and then it feels like there wants to be a 4 there, and you can do it from both sides. So we can use the graph and the outputs and see what we're getting closer and closer to. That's a great strategy in a problem like this, when you have sine x over x, and we have what's happening as we approach 0. Let's get this out here. So just looking at this, you may have no clue. You may be like, I don't know what's happening as we approach 0. So if I ask you, where's the limit as x approaches 0 of sine x over x? But look, the graph, and if you use the left hand and the right hand, it looks like we're getting very, very, very close to 1. So that is a great strategy. If you are lost on a limit, plug it into Desmos and go and look at it. But on the AP tests, they're not going to give you more of these graphical ones. They're going to want you to do it either algebraically or using L'Hopital rule. So in class, we're going to practice the algebraic techniques. So I want to remind you of these algebraic techniques. So here are some algebraic techniques. Algebra techniques. The first one that we really hammered home last year was our good old, this is a case of factor and cancel. Try to factor, try to cancel. If you can factor and cancel, then you're in a good position. Because it's essentially you're removing the discontinuity. It's called the removable discontinuity. It's how it's where the holes are in a function. So if you can cancel out a term, that means there's a hole in the function. And I already told you limits exist at holes. So you can try plugging in 2. You get 0 over 0. 0 over 0 is actually a very good thing. We can use L'Hopital's rule, but I don't want to do that yet. I want to try the algebraic technique first. So in other words, let's factor the top using difference of squares. So x plus 2 and x minus 2. The bottom doesn't factor. Sometimes it might. Bam, bam. Once you do that, now you can plug in. And you end up with 4, just like we thought. So that's an algebraic technique, factor cancel. We'll practice a bunch of these in class. If you want to see more of those, you can look at the other videos. But I'm not going to do more of those. We know how to factor. What about a problem like this? I bet this will remind you of some things we did last year. What if I asked you about the good old this type? All over x minus 5. Here's another one where we can use an algebraic technique. It's called multiplying by the conjugate. So that's the trick where if you see a radical, first you could try plugging in 5, you're going to get 0 over 0, which means you can try a strategy of multiplying by the conjugate. 2x minus 1 plus 3 all over square root of 2x minus 1 plus 3. Remember, if we have a fraction, we can multiply the numerator and denominator by the same thing because it's like we're multiplying by 1. I go into this detail a lot more in the other videos, but just quickly remember we are foiling or double distributing. You end up with 2x minus 1 because when you multiply a radical times itself, the radicals cancel. 2 middle terms cancel when you have a conjugate, and you get minus 9. All over. Don't multiply these ones together. You can keep them separate. Now, something nice should happen in problems that are designed to be done this way. Notice the top becomes this part. I'll do it right here. becomes 2x minus 10. And lo and behold, you can do a common factor of 2. And how nice, we actually get to cancel something out here, and then we can plug in with no problem. So notice, boom, boom. Now you can take 5. You can plug in 5. It looks like we ended up with 2 over square root of 9, which is 3. 3 plus 3 is 6, or 1/3. And if I wanted to, I could go graph it and show you what the graph looks like, and I guarantee that there would be a removable discontinuity at 1/3 in the graph of this. So that's factor and cancel. This strategy is called multiply by the conjugate. But the most important one, and the cool thing about BC is now we can use this at our disposal anytime we want because we know what a derivative is. When you first learned about this in AB, you didn't know about derivatives yet, so limits were a little bit trickier. But the end-all be-all greatest go-to clutch maneuver is not to use canceling strategy. It is to instead use good old L'Hopital rule. L'Hopital's rule is an amazing strategy for evaluating limits that end up existing. So if there's an asymptote or there's a jump, the limit does not exist. But if there's a hole, we know the limit does exist, and that means L'Hopital's rule probably is going to apply. So if you go back to the previous problem, the first one, I will remind you of L'Hopital's rule, and you should always have it in your back pocket. Always, always, always have L'Hopital's rule ready to go, because so many of the problems on the AP test are just applications of L'Hopital's rule. So this is one where if you have to show the work, and this is one of those things where I graded on the AP test, they are very, 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 very particular about how you show L'Hopital rule. Here's how you need to show it. You need to show that when I plug 2 into the numerator, I get 0. You need to show that when I plug 2 into the denominator, I get 0. You can then jump to this, not an equal sign, an arrow. If you use an equal sign, they'll mark you wrong because it does not equal 0, 0, 0 over 0. It approaches 0 over 0. Then I might mention that you are using L'Hopital's rule. You technically don't need to do this because if you do the math, they'll know what you're doing. Now you can use an equal sign to show that this limit is the equivalent to the limit you would get when you take the derivative of the top and bottom separate from each other. Derivative of the top, it's been a minute, but that is a power rule. It's 2x over. Derivative of the bottom is 1. And now you can use an equal sign because that limit really does equal 4. Okay, this is one of those things that I'm going to hold you to pretty quickly. I need you to show me the numerator equals 0, the denominator equals 0. Therefore, the limit tends to 0 over 0. You're using L'Hopital's rule. This limit equals the same as this limit here, and then you can give me the numerical value. Okay, L'Hopital's rule is going to be incredibly important for going forward in this class. I'm trying to see if there's anything else I want to go over. I don't think so, but maybe. 1 second. Nope. We'll talk about end behavior. That's the other one too. I don't know if I want to do that here. Limits to infinity. We might go over that in class a little bit. There is one down below. Do you remember that these types of problems, the limit as x approaches infinity of like 4x cubed plus 7x minus 3 over 5x cubed plus 2. Let's say that, for example. So this is an infinite limit, a limit that approaches infinity. This is just asking about end behavior. We will do a ton more of these second semester. So that's why I'm not too worried about them right now. But if you remember your rules, you're just looking at the biggest power. Really what you're looking at is which function grows faster, the numerator or the denominator. If the functions are the same power, at infinity, they're going to level out, which means they level out at the leading coefficients when you divide them. You can graph this and see that there'd be a horizontal asymptote in this case. What about if the powers don't equal? Well, let's say that the power is bigger in the numerator. So 4x to the 4th plus 7x minus 3 all over 5x cubed plus 2. That means the limit is either infinity or negative infinity because you have a bigger power in the numerator. So it's always going to either be this or this. And this is the trick where you can ignore all this stuff. If I'm going to positive infinity, just think about what happens if these are really big positive numbers. This would be a positive to the fourth, which is positive, divided by a positive cube, which is positive, and the coefficients are positive, so the answer is just positive infinity. That was the trick we did last year. If you forget, there's a video that's more in detail about limits as we approach infinity down below. And then the last case would be what happens if you have a limit as you approach infinity and the bigger power is in the denominator. This is the easiest case. This just means as x gets bigger and bigger and bigger, the bottom is going to be way bigger than the top. So in other words, you can almost think of it as like 1 over infinity. And if the bottom is infinitely big, this approaches 0. All right. So those are infinite limits. We do a lot more of these second semester when we get to infinite series and all kinds of stuff. I guess the most important thing to remember is probably L'Hopital's rule and these visual ideas. Okay. Remember, limits exist at holes. They do not exist at jumps. They do not exist at vertical asymptotes, aka infinite discontinuities. And in order for you to tell me something is continuous, you would just show me that the limit equals the function value. All right, I think that's good for now. That's it. Bye.